Hello students, this is the video that will cover the rest of section 4.1. So last class we left off on problem 3 or example 3, and we were graphing the two functions that we have here, 2 of x and 1/2 of x, which we also discussed that one could be written as 1/2 to the power x. And the graphs, we have them here on the right side. So we have the graph in red is increasing, and that is because the base is greater than 1. The graph in blue is decreasing because the base is right here, 1/2 to the power x, which is the same as 0.5 to the power x, and we know that that is less than 1. So if the base is less than 1, the graph will be decreasing, but still positive, always greater than 0. We also call, when a graph is increasing, like the one in red, we call that exponential growth. And when the graph is decreasing, like the one in blue, we call that exponential decay. So we compared them, and we said that they both have x as the exponent, they have the same y-intercept, they're above the x-axis, they have the same domain and range, and they also have the same horizontal asymptote that will be right here on the x-axis, or is the line y equals 0. So we're gonna graph the ones that I have here, and so I graphed those on decimal so we can get a better picture. So the ones for part B are 3 to the power 1 minus x and 3 to the power negative x. So first I'm going to show you how they look. So we have there 2 to the power x. You guys can see that it has the same y-intercept. And just to review the concept that if the base is bigger, like that one that I just graphed, 3 to the power x, you could see that it is increasing faster. You can see if we were to trace a line on it, it will be like a slope, it will be steeper. And so now I'm going to get rid of that 2 to the power x. And if I graph 3 to the power negative x, that will be like the same graph in black, but reflected across the y-axis. And they both have the same y-intercept at 0, 1. So now I'm going to get rid of the 3 to the power x graph, the one in black. And so that is the one that you guys need to graph for your on your paper. So you could trace the y-intercept. You could also trace, this is a good point, -1, 3. I can't really get to find it, but you could see it, it's right there. So trace those two and then draw your graph on the paper. Now this is how the graph of 3 to the power 1 minus x will look like. And that's that graph in blue. So the point that used to be the y-intercept for a graph in red was shifted 1 unit to the right. And you could see that point right there. So it's going to be at 1, 1. So you could graph that point and also this one here, 0, -3. And the point, actually I can type it here, 1, 1. Right there. And that one. So that is how the two graphs will look. Both of them are decreasing because the exponent is negative. Now, having a negative exponent, we could also represent that graph as a fraction, and it will be 1/3 to the power x. And you see that one is the same graph as 3 to the power x. So right there, I have those two graphed there. That's just 3 to the power negative x, and if I graph 1/3 to the power x, it's just going to be overlapping the other graph. So the two that you need for your paper are those two. Okay, so we're going to move on to the next problem. And let's see what we have here. So example 4 is the function that we need to graph is 2 to the power negative x squared. And in fact, this is a very famous graph, and it represents the normal curve. So in statistics, this is used a lot. And if you were ever tested and your scores were compared to other students' scores, if you were average, you will tend to stay like right here, like in the middle of the curve. And then the low performers stay here. The high performers stay over here. And you know, this is divided into the mean and the first quartile and etc. So right now the only thing that we're gonna cover about it is that it is an exponential function because x is part of the exponent even though it's being squared. And so if we were to complete this table, which I'm just going to write down the values, that's how you will graph it if you didn't have the graph in front of you. So you will enter on your calculator 2 to the power, and then in parentheses I will enter x and then to the power 2. And then of course you press enter. So if you do that and then you look at the table, then you can get some of the values. Typically the table only shows you the ones for integers. So for the other ones, you will just have to enter on your calculator. For example, to get this one here, it will have to be something like 2. Oh, and I forgot the negative sign here. It will be 2 to the power, and then I will use parentheses, and then I will use the negative sign, the little one that is in parentheses, and then instead of x, we will substitute that with this number. And you could see that that one is negative itself, so I'm going to put it negative, and it will be negative 1.5, and then I will square that like that. So that's how you will enter it on the calculator. This is the x value that I am replacing. This negative here is coming from this negative. So I'm going to write down the values to save us some time. So it's 1 over 16, 0.21, 1/2, 0.84. For 0 it will be 1. For 0.5 it will be 0.84. For 1 it will be 1/2. For 1.5 it will be 0.21. And for x equals 2, the output will be 1 over 16. So those are the values, and if you if you plot all those points along the graph, that's what you will get, the bell curve. Okay, so let's move on to the next problem. Actually, I'm going to stop recording here so the video is not too long, and then I will record a second video.